For our BRAE 128 quarter project, our group chose to complete the soil compaction experiment. To complete the experiment, background research was conducted on the formation, composition, behavior of soil, and resistance processes for bioresource and agricultural engineering professor Dr. Sadek, and an experiment measuring soil compression was conducted in Lab 4.
Soil maintenance, especially in the agricultural field, is essential to the sustainability of crop production. Dr. Sadek specializes in machine biomaterial interaction and soil dynamics, and while working in the soil and agricultural industry, he questions the resilience of soil when compacted by livestock, or more specifically, cattle.
Our client has expressed interest in this project because of the overall lack of investigation and experimentation that has been completed. The history of soil behavior dates to the beginning of agriculture, and although some research has been done regarding soil and heavy machinery compaction, it is crucial to note dynamic nature of our agricultural fields.
Variations of this experiment have been conducted in the past. Therefore, the materials necessary to complete this particular soil compaction experiment have previously been fabricated. Specific components of the experiment include the compaction box and the compression mechanism. The final design shown was chosen by our group based upon its low total cost of fabrication, overall safety, and ease of use. The compaction box, a steel box fabricated by previous students, represents a soil profile prototype, in which 3 layers of soil compaction are displayed through a fiberglass wall. The levels of compaction include high compaction, colored darkest green, medium compaction, and lowest compaction. The layers located above the high compaction section, medium compaction, and lowest compaction are created by receiving the appropriate amount of force from the metal sheet. This amount of force ranges from a minimum of 1,100 pounds to over 2,500 pounds. Each layer after compaction should measure between 2 to 5 inches in depth.
To conduct the experiment, a sufficient soil sample was collected and properly sifted to represent the variable of interest or the soils of the San Luis Obispo area. The quantity of soil collected is dependent upon the experimental design. For our purposes, 30 liters of soil were collected from the crops unit of the Cal Poly campus.
The basic procedure for machine compression are as follows. Activate compression mechanism computers once the prepared compaction box is placed safely on the platform. A prepared compaction box includes a properly weighed and measured layer of soil. Confirm that the metal sheet is centered above the opening of the box. This should cover most of the open surface area. Then, close the protective glass. Select the optimum range of force and depth, should never be more than 7 inches, and activate the machine. To activate, select the blue tear option for both inch and pounds in the auto tearing area of the screen, and the gray max reset option in the max values area of the screen simultaneously. Do this until the corresponding red rectangle value reaches 0 or close to, and select the green start option in the bottom right of the screen. Then, push the green button on the console and apply steady pressure to the release lever. As the machine begins the compression process, it will raise the platform to the compressive object. Record observations during the compaction process. Properly power down the machine by pressing the red button on the console and returning the release lever to its starting position.
This same process will be repeated when using the metal cone for the cone penetration process and the cattle hoof. When conducting the cone penetration process, we simply replace the compression sheet with the metal cone by loosening and retightening the bolts that secure it. Finally, to measure livestock compression, we placed a 3D printed hoof directly underneath the compression sheet and placed even pressure until reaching a desired amount of force.
The data collected included soil mass, soil height before compaction, height after compaction, load applied, and cone penetration test. Notice, the data recorded for the cone penetration test is the same as the load applied. This demonstrates the accuracy of the test as a measurement of compression. Though our presentation only shows data from one trial, we conducted 3 to minimize any confounding variables in the experiment. For example, the moisture content of our soil sample dramatically changed from our first date of experimentation, November 3rd, and our second date, November 14th, almost 8%. The second half of our experiment included compaction by a 3D printed cattle hoof. As mentioned before, we used the same metal sheet compression procedure, only with a cattle hoof replica placed directly underneath. As this was essentially the focus of our term project, it was incredibly important that we replicated a minimum of 3 trials.
The applied load hoof is the amount of force applied by the hoof. Notice the maximum amount of pressure we chose to apply was just under 500 pounds, which is equal to about 1/4 of a market-ready steer's total weight. The applied load cone penetration is the amount of compression found when the cone penetration method is used. When the cone is pressed into the area most affected by the cow hoof, it records the amount of compression that has occurred.
The data collected from this portion of the experiment demonstrate the variation in compression that can occur in livestock production. To illustrate, a young steer cow that weighs 748 pounds, dispersed fairly evenly throughout 4 points of penetration, or 4 legs, may only apply 187 pounds of force per hoof, but is responsible for almost 460 pounds of compression. It is essential to recognize such disparities when questioning soil nutrition. More specifically, a farmer could be raising cattle now, but may decide to sell to a business that specializes in orchard production. The physical composition of the soil might be so altered by the consistent but sporadic compression that a change in production would be so detrimental. Soil is a finite resource, but agriculture is an ever-adapting branch of our society.
To guarantee the success of the future of agriculture, agriculturalists must take into account the seemingly insignificant effects of such simple ranch hand practices.